Right, it looks like it's quieting down out there, so I think we'll just start because we have a lot of material to go through. Welcome. This talk is called Theory Makes Beautiful Programs. I'm very happy with the title. Quite happy with the talk as well. It is, I mean, Kate already wrote it up in the keynote, and it started out as a reflection of what I've been doing for the past few months, and the inspirations and literally sources that led to it that I wanted both to highlight and also some of the insights that kind of came out of it as to how we develop software and how we're sometimes doing it wrong. The topic is going to be on MCDC, which is a terrible name. It's an abbreviation for Modified Condition Decision Coverage. And quickly, I'd like to do a poll, like what industries people are from. So anyone in aeroplanes? Ish. Okay, good. Automotive? No. Rockets? Things that blow up? Yeah. Okay. Good. Other, I don't know, vision, I guess. Any more interesting industries? Some defense. Okay, good. So it's kind of good because that means you've probably not been very exposed to this. And I would start really by pointing out that MCDC, or coverage in general, or condition coverage in general, is probably one of the most overvalued and still underused testing criteria that we have. So we're going to have a very quick one on that. If you want a more sort of hands-on tutorial and introduction to it, I recommend coming to my other talk in a few hours, where we'll be a little bit more on the action. I'm going to do a thorough description of an algorithm I designed in order to implement support for this type of coverage in GCC, and some ramblings on thinking before typing. So let's start with the MCDC. So why do we care about coverage? What is it? Why is MCDC different from the branch coverage, which you may or may not be familiar with? And what does mass have to do with all of it, right? So one reason to care, if you're in one of the industries in particular I mentioned, is the lizard people, which I would like to call the regulatory bodies. So if you develop software for planes or cars or anything that moves or may not kill people by accident or on purpose, you might have to obey to these regulations. And so DO is, I don't know what it is, but it's for the aerospace, it's the FAA, I think, that ratified it. For their safety critical, like level A software, they mandate that 100% of your code has to pass this criterion. For the highest safety levels in cars, and that's typically those that deal with the functional. I mean, you don't care if your music player stops, but you do care if your brakes stop working, right? They also have to be tested to the same criterion. But I think even then, it's underused in the general industry as a sort of specific probe. We're going to very briefly cover the problem with branch coverage, and I've picked a way too light color for the highlighted rows. Is that in order to satisfy branch coverage, you need two tests. And the problem is here that you have way more than two inputs to this decision, right? Notably, you never actually test if A can be true. And then you go like, oh, I mean, it's a Boolean, so obviously it can be true, but it may or may not be true if that's the case, or if you have broken parsing because you're dealing with I/O, right? So it can be deeper than that. Formally modified condition decision coverage is satisfied if every entry and exit point has been invoked, every basic condition has taken all possible outcomes, and each of the basic conditions have been shown to independently affect the outcome of the decision. So the first point, every entry and exit point has been invoked. This is branch coverage, right? So what we can do is, I mean, this is branch coverage. Everyone, like, have you been in the then? Have you been in the else? Condition coverage is have you passed true and false to each one of the variables you put in. The independence criterion is what makes it different, and it's a little bit hard to see, but there are different rows highlighted for every table. And it's this independence criterion that makes it strong, and actually that makes it interesting. So of course what you can do is you can test a power set of inputs, but the thing is it wouldn't actually give you more information about the behavior of your inputs or of your program. The motivation is it requires n+1 test cases rather than 2 to the power of n. And what happens sometimes is, I read in a paper from NASA from early noughties that they'd found some cases in the wild in avionics where there were 36 conditionals in an if. And who does that, right? But sometimes you have to because of rules like Robert touched on yesterday. And interestingly, you can catch some pieces of bad logic with MCTC. Of course, the problem is it only tests the implementation and not the spec. So if your spec or your algorithm is buggy, it doesn't matter if your implementation is correct because it's still the wrong program. It's possible to cheat it with restructuring. We won't have time for that now, but we'll do that in the other one. And if you look at it as a whole program analysis, you're going to have to, in order to actually achieve full coverage, you need a lot of test cases in not very interesting pieces of your code base. Also, it's awful to do without tooling. It's absolutely awful. So I wrote a patch for that, for GCC, which the work has been paid for by Woven Planet, where I'm employed. In total, it tallies up to about 3,000 lines. Approximately half of that are tests. Some is documentation, there's a little bit of I/O. The interesting changes are in the tree profile file, which have 978 additions, and about a third of that are comments, like high-level descriptions. So I think that the total ends up to be somewhere between 400 and 600 lines to implement this, which is actually pretty dense, largely because GCC has some good internal interfaces, but also because the program is short. So this is what it looks like when you do it, right? So you compile it with profile conditions, you run it with your inputs, and then you run gcov on it. And then it will tell you what conditions are covered and what conditions are not covered under this criterion. So the question is, you obviously run this with A is true in the third demo line, right? Why isn't it covered? Any good instincts? Yes. Yes, exactly. It's because B is false, which is kind of unintuitive, right? Because, I mean, you have it in the input, but it still doesn't get counted. Why not? Because of this criterion here, it has to independently affect the decision. And it turns out what we're witnessing here is something called masking. So if you look at this table, and again, it's almost impossible to see the blue, but it's line 1 and line 5. They've been highlighted. And you can see in the A column, in the first case, A is false, and the other case, A is true. But the outcome, the decision is still false in both cases. So obviously, changing the value of A didn't matter at all. It didn't change the outcome. So it's not independently affecting the outcome in that case. It's called masking, and it happens on the right-hand side of conditions. So in the next talk, we're going to go through a lot of this. But very quickly, the observation is that if you reverse the expression, those masks become short-circuiting. Obviously, because Boolean expressions commute, then you can reverse it without actually changing what values it will accept or not, assuming you have no side effects, of course. So this we're going to go through later today. So let's talk about writing beautiful programs. Because what I realized when I did is I started solving for the simplest of cases. Like literally my first test case was if A, right? Which is already covered by branch coverage. Because there's this general idea that if you're targeting a general solution, it has to always also solve the special cases and the simple solutions. So you can start by doing those and drawing some insight. And eventually you add another test case, and this is all a classic TDD. Then you write the stupidest implementation possible because you know you're going to have to change it. That would solve this problem. And then you walk back whenever you get a failing test case and you start understanding why. And that is not about twiddling, that array access or, inverting a case. You need to actually understand why doesn't this work from a sort of higher level. And what happened was that the more I started to try this out, the more confident I became is that both the approach is viable and was correct because it started being based on set theory. and a little bit of graph theory. Very like entry level, but you know, and it turns out set theory works, right? And the program kind of wrote itself, because once you had that description of how things interacted with each other, the program just falls out. So credit where it's due. The title and the idea for the talk I nicked from Russ Cox, right? Who has this great post from sometime, I think in the 90s, which is called Regular Expression Matching Can Be Simple and Fast, and the tagline is, but it's slow in Python, Perl, Java, you know, he lists a bunch of languages. And in that, he uses, he discusses a theory called, he uses automaton theory to implement regular expressions, and it becomes a very nice program, reasonably short, quite easy to understand how it behaves the way it does, and he does it in very plain C, right? And for the GCC patch, this has been a bunch of mostly simple relationships that I've just stacked on top of each other, right? So we're going to go through those. So let's start with the control flow graph. I would say that there was published an algorithm in 2009 or 13, I can't remember. I think it's 13. That describes figuring out condition coverage from abstract syntax trees. My algorithm does it on control flow graphs. So it's a little bit different. So the program on the left here it's pretty simple. Will in a part of as a compiler transformation will be translated to something that is pretty similar to the code on the right. You know, you have your label A, and then there's a series of single condition go-tos, right? Single condition tests with a go-to. And this is what the compiler very quickly sees. So when it does a lot of its optimizations, it happens on an intermediate representation that looks pretty much like that. In GCC, it's called Gimple and RTL, and maybe one more. LLVM obviously uses LLVM IR, and they're experimenting with another one for C++, I think. And if you draw it as a graph, this is what it looks like, right? Formally, the control flow graph is a directed graph where nodes represent uninterruptible sequence of instructions. So if you have a bunch of arithmetic, they're going to be in the same node, right? There's no control flow in arithmetic. Edges are the next possible paths of the execution, and they are labeled fall through, true or false, or conditional when you group them, complex. There are a few more that are used for different kinds, but they're not really relevant for this. And the final property is very important, is that fall through and conditional are mutually exclusive. Fall through just means continue to the next node. There's no decision to make. Whereas conditional, obviously, you can go either way, right? So the first thing we need to do when presented with a control flow graph is we need to infer the decisions. We need to figure out what exactly are the Boolean expressions. Now, unlike the AST approach, you don't actually have the concept of a Boolean expression or even the concept of an expression anymore. You have the flow of the program. So this is what we want. This is the goal. I have, for the case, just for illustrative purposes, added the entry node that you will find in all control flow graphs, but I've omitted it from the rest of the slides because it's not really relevant. You can just assume it's there, or the previous section of the program, or the previous something is there. But what we want are the three nodes A, B, and C, right? Because from the source code, it's obvious that that's the expression. And if you ask the AST, then the AST will know that this is the expression, right? From here on, it gets a little bit heavy on the notation. Please interrupt if something is very alien. I'll try and make it as understandable as possible, but we need it to be a little bit dense. Now what this says is, so this is the first, after I started doing the maths on this, this is one of the first things I realized, and it turned out, after a little bit more work, that this is probably the key observation that makes this algorithm work. And like when you say it out loud, it sounds so obvious, right? And it pretty much says that for all of the nodes that make up a Boolean expression, the B is one Boolean expression, right? Then the edges or the successors of that will have to be in what's called the closed neighborhood of B. Now, the neighborhood of a node or a subgraph are all the nodes that you're able to reach from that graph, right? So it's a common thing in computer science. And I mean, the neighborhood is in other ways defined as the Boolean expression itself, the node that make up the Boolean expression, and the outcome of the expression. So the start of the then and else blocks, right? And what that really says is that within a Boolean expression, you can only evaluate or keep on evaluating the Boolean expression. You can't really branch off to anywhere else, right? So if you look at that in source, it means that when you start evaluating the if here, you have to continue to either you end up in one of the outcomes or to the end of C. There are no other way. You can't go anywhere else. This is not true in general, especially in C++, because you have exceptions, but exceptions don't contribute to control flow coverage because you wouldn't finish evaluating the expression, and so they're ignored, leaving us with a much simpler graph. We're simply ignoring them. But other than that, like, they can be considered interruptible. Now, that's what this Greek thing means, right? This is the same proposition, slightly restated in the context of edges. And it says that all of the edges that originate from one of the nodes in a Boolean expression will go to either another node in the same expression or one of the two outcome nodes. And it's a really long way of saying you have two outcomes of a Boolean expression, right? Turns out this is actually a very key insight. So in this drawing on the right, you have the outcome marked in gray and the nodes of the Boolean expression marked in blue, right? Another property of that is that all of the edges within a Boolean will be conditional, right? Again, that's not completely true because you can have function calls that will then evaluate one of the Booleans, but that will just be a long chain of single fall-through edges that can be contracted. So you can simplify that to, being one long conditional edge, right? So again, the maths work out. And then the final insight from this is that if you look at the last term in a conditional expression, it has to decide the outcome. So you have short circuiting, and the outcome can be decided by pretty much any of the nodes, right? Or any of the terms in an expression. But if it's not decided by C, C will make a decision for you, right? It sounds so obvious. It is so obvious. And what that means is that the successors of the last term in an expression in the graph will always be to the two outcomes, whereas the short-circuiting edges will be to either of the outcomes, right? Put another way, it means that you can't have a goto that will end up in the middle of an expression, right? You can't put a goto or a label in front of B and go to it, right? It doesn't work because the expression is an atomic unit, right? Okay. So that gave me the first draft, for the first phase, and it's a BFS, right? To do a breadth first or depth first search kind of doesn't matter. So we're going to do that now. This is the graph. You start with A, and you say, okay, this is a condition edge. So we get B. And what we want to do is we want to gather all the nodes that we can reach by following only condition edges, right? Okay, we can reach C, condition edge. We can reach T with a condition edge. We can reach C, but we already have collected C, so we ignore it. We've already collected T, so ignore that. We can reach F. And that's really it, right? Because you see both false and true have a single edge, which means that they're not conditional, they're fall through, right? So we stop searching. This is what it looks like with the cases that you need to check in order to handle the complex control flow graph thing in GCC. Make a queue, and while there's something in the queue, from your starting node, check through its successor, right? If you've already seen it, throw it away. If this is you, skip it. If it's a back edge, so typically loop edges, right? Or at the end of the loop, you will have a back edge to the top of the loop. Ignore those; they don't matter. There's a dominated relationship, which we're not going to go into now because it doesn't really affect anything at this point. And added to the queue. I mean, this is a BFS, right? Okay, so we have a slightly different program where the C is not an OR in the if, but it's in the outcome block of the then, where it's a single conditional, and the control flow graph for that is on the right. So this is one of the, I think this is the 5th test I wrote for this. So we do the same algorithm. Okay, from here we can conditionally reach R and B. We add those. Then we try and add C and E, but oops, C is not a part of the expression, right? So it turns out the simple BFS is not sufficient because, I mean, the program on the left there is a pretty common program, right? And not handling that is not an option because we shouldn't include C in the set. We want it to just be A and B, right? So I took a step back and I realized that what the BFS gave me was a cut. Okay, so a cut is a graph partitioning where you can almost imagine a line that goes through the past the red nodes, or edges going into the red nodes. That is immediately reachable with this BFS, and then those adjacent to that, because we're in this neighborhood thing. Remember the identity from before. And then we have an observation turned out to be very useful. And is that for all the edges in the cut, or in the whatever we find by reach, right? So the reachable ones through conditionals, they will all be conditionals. And what that means is that our outcome will be a part of what we can reach, right? Because there has to be conditional edges into the outcomes. This is just a very precise way of saying that. What that also implies is that the graph we're searching for, the expression we're searching for, has to be a part of what reach can find, right? It might find more, so what we now need to do is essentially filter this. And then you notice that there's not really a path from the then block to the else block. And there is a teeny tiny edge case with go to with nothing that I think actually is a control flow graph construction bug in GCC that will maybe violate this, but for the most part, you're still interruptible within the single Boolean expression, and it always has two outcomes, and there's no real communication in between, right? And if you formalize that, you will see that what these have in common, if you take this picture and you would reverse the edges, you will see that the only way to get into C and E, for the most part, when starting at, or actually when starting at A, the only way to get into then and else is to evaluate all of the expressions, right? And both blocks have the leading or the conditional expression in common. Now, formally, it means that the ancestors to the then, for all of the nodes in the then, the Boolean expression will be a part of its ancestor set. So if you take any node in the outcome, like in P, and you walk it all the way up to the top of the graph, B will be a part of that, because I mean, in order you're able to reach the then block from the Boolean expression, right? That's why we have it. And this is pretty cool, because they both have this property, right? Both the then and the else. In a way, you could flip the arrows here, and it would be just as valid, right? So okay, let's look at that. Let's look at the ancestors from Q. Well, it's C, B, and A, right? You can, like any path that will go into Q might go through, or even have to in this case, A, B, and C. The same applies to P, right? Which makes sense because they're both the outcome of C. But R has A and B as its ancestors. And what turns out is that this is a very good way of figuring out what these have in common. Like if you look at the neighborhood, which is the first thing you get that isn't a conditional, right? If you take all of those ancestors and see what minimal set of ancestors do they have in common, which is what the B equals line there, big cap, says, that will give you the Boolean expression, because that's the only thing they both will have in common, right? There's a problem with that, because our BFS needs to start at the topmost node, right? It has to include all of the expression, which means it has to start from the top. And the solution to that is actually remarkably simple, is that you can just traverse the graph in depth first order. So if V is just if a node you're evaluating is just a fall through node, mark it, skip it, throw it out. If it's a conditional node, it's the first conditional node you're getting to, so it has to be the leading term, right? So you do this scan, this reach and then filter, and then you mark it, right? And say all of these have now been processed. And if it's already marked in the DFS search, it means that it was already processed by an earlier leading node, so it's an internal node in a Boolean expression, and you go through, right? So I was thinking about this for a while. Can this lead to problems? And it may lead to expressions being processed out of order, which means that if you have a long program, it might, it might process deep inside, like either inside the block, in the else before the then, so it might not be completely in the order of your program from top to down, because it depends on how the order of the edges in the control flow graph representation, but it doesn't matter because each of those are independent anyway. So you know that the expression, the isolated Boolean expressions themselves will be processed in the right order, and then you don't care about the program being processed in arbitrary order. If you put that together, you get this. And this is pretty easy to translate to the C++ dialect that GCC uses, right? It's not a very complicated program. It's 2 loops, right? And this is defined decision. This is where you start by doing a BFS. If it's just one node in the BFS, then it's fine. It's a singleton, it's a single if, so you just throw it out, or you just return it. But if not, you have to do this thing where you collect all of the ancestors of each of the nodes in this neighborhood, which are the deepest possible candidates, right? And then you take the intersection. This is that function as it's implemented in GCC minus the setup, and actually minus the setup. The teardown is there. So what's that? 15 lines, maybe 20, something like that. And this, it kind of materialized, right? And what's nice about this is that all of these operations are pretty high level, and they map one-to-one to the relationship between the graph and the outcome, right? So you have the ancestors of function. It collects the ancestors, and then you do bitmaps for sets. That's really it. Any questions? It's GNU style, so my apologies. I don't like the GNU style. Okay, putting that together with the whole program analysis, you get this. You just do this in DFS order and then collect each of them. So now what you have when you run this program, this too is pretty easy to translate to C++. When you have this, it's like, or rather when you have this typed up this way, the implementation just falls out. It's remarkable. Okay, so let's talk about masking. And I did not actually expect anyone to get it right that wasn't from one of the three aforementioned industries. But masking happens when it turns out the left-hand side doesn't matter because it doesn't change the decision. Because and that happens when the right-hand side of an OR is true and the right-hand side of an AND is false, right? And then false, it'll always be false. So the first observation I made there is, or pretty early on, is that Boolean expressions are isomorphic under the operator. So these are the two expressions and their respective control flow graphs. If you just invert the labels, you get the same graph, which is pretty neat. So I wondered why, and this is where the theory comes in, right? Because it's fine that they have this property, or they seem to have this property, but why? Understanding why means you can leverage it. And the proof is really just say De Morgan and then go out of there, get out. That they have to be. The implication of that is that we actually don't need to understand the operator, unlike in the AST approach that was discussed by the University of Minnesota, Wallen and friends. You only need to understand the shape. So if you look at when masking happens from a control flow graph perspective, it's very briefly, masking happens, or rather, a condition is independent if you can give the same input vector, change that one variable, and while keeping all of the other elements in the vector fixed, like the function inputs fixed, and have the decision be different, right? And it turns out in graphs, this happens when taking another path still ends up with the same node, right? So when you have a branch, you can either go to the true or to the false. If you go to the false, but you keep on making the choices you otherwise would have made, you end up in the same node. So I have an example of that here for A or B, right? On the right hand, the right one you can see goes through B but still ends up in true, right? Because B was set to be true. In the middle one, B was set to be true, but it was never evaluated because it was short-circuited. And this is actually a key insight. Because masking can only happen at nodes that has multiple predecessors, right? And if you have multiple predecessors, that means that you are the destination of someone else's short circuit. An implication of that is that we know where to start looking for masking effects, right? Because remember, when you're looking at this from a compiler perspective, you're giving an arbitrary graph. You don't really know how you got there. All you can do is maybe recognize the shape. So a little bit of repetition from, I guess, sixth form is the association, right? Under the same Boolean operator, you can remove the params. Doesn't matter, doesn't change anything. This actually turns out to be very useful, because that means that you can take any Boolean expression and rewrite it into an alternate or canonical, and I actually don't have a good name for it, form, where you have a chain of operands with no params, and you have the params every time the operator changes, so you kind of get this nesting effect, right? And it turns out that if you look at the control flow graph, that will be represented pretty much exactly like that. That's how the control flow graph gets constructed because of this relationship. And masking will propagate until the operator changes, right? So in this case, if you have D equals true, then it doesn't matter what B and C are because the parenthesed expression, the sub-expression will always be true, right? But A, like an AND expression, will never be masked by its right-hand sign being true, right? So A is not masked, but B and C are, because there's an operator change, right? However, the outcome of a sub-expression as a whole may still mask outside of this. Again, this is not very, if you just look at the proposition, it's very intuitive, right? because you can do substitution. So if we would substitute B or C for F, and then write it as A and F, I mean, it's obvious that F can mask, right? So if C in this case would be evaluated to false, that actually also implies that B is false, because otherwise C would be short-circuited and we wouldn't have this problem in the first place. But it would then also mask A. However, C will not mask B, because you have to have a false B in order to get there in the first place, and you're never masked from the left-hand side. So this kind of follows from the observation from before, is that S omega means the last term in S, right? S is now a sub-expression, whereas B was the full Boolean expression. Now, the last term in a sub-expression can short-circuit in the super-expression. And that kind of follows from the same thing, where the last term in an expression will have to decide the expression, right? Because there are no more terms to the right of it. So I came up with this funky way of drawing it, where you actually draw it in nesting levels, right? So on top, you will see it drawn in this alternating form. And the lower figure is where you're drawing this as the operator alternates. So you can imagine in between all of the terms in the top row, there will be ands, and there will be ors in between the second row, and then ands again in the third row, and it will go, and it would alternate. And when you put it out on a paper like this, you actually get some interesting things you can do with arrows. So if you make C true or H true, you will see how short-circuiting works, right? Because you basically move one level up and go to the next one on the right. And it doesn't matter what level you're at, because remember that this propagation is firewalled by the change of the operator. When D is true, in this case, it will keep on evaluating E, because the sub-expression C or D is evaluated to true, and true does not short-circuit and, right? It keeps on evaluating. But if D is false, it short-circuits all the way here. But if D is false, it will also do one more thing, right? Because it will mask A and B. And there you have this interesting effect that when you see a lower level short circuit its super expression, then there will also be a masking effect, because you're now with the wrong value at the right operator, if you will, right? Turns out this observation is very useful. So when you're evaluating a condition, you have two possible outcomes. Like either you short circuit the right operands, or you keep on evaluating. Right? It sounds silly to have to repeat it, but it's actually very useful. And the implication here is that if one of the edges is short circuiting, the other one has to be a masking edge, right? Because this relationship is so intimate. And now we can finally state our problem, right? So given a pair of incoming edges, which one is masking and which one is short-circuiting? How can you tell? And the implication is we kind of need, or rather what we would get from being able to answer that is an ordering, where if you have two nodes, then one is less than the other, if it's a left operand, right? Because it has to go that way. And it's greater if it's the right operand within the same expression. Any idea how to figure that out? So the solution is topological sort, which is really just a DFS. Like you do a depth first search and you record them as you go. So now we have that, right? This relationship will give the implication here is pretty much the definition of the topological sort, right? And writing a topological sort is easy because you go to Wikipedia and you search top sort and you copy it from there. Okay, so now given a pair of nodes, which happen to be the predecessors of a third node, right? Then you will be able to compare them and order them, right? Then you will have that the lower one of those will have to be some sub-expression's final term or last term. As an implication of that is that you now also know the outcomes of that expression. And just for the notation, S is one of the sub-expressions of B. So just go back here, then S could be G or H or N, I or J or something, right? Any of these. Most of those are single term, but you have a couple of multi-term ones. And the other implication is that the other one then taking the M, taking the higher one, the deeper one in the graph, when you take that one, that the nodes in S will be masked, right? So a bit of repetition is that the closed neighborhood of B is just, pick all of the successors of the nodes in B. That is assuming you know B. Then you get the closed neighborhood, and the open neighborhood it's the outcome. So anything that was true for B, the full Boolean expression, will obviously be true for a sub-expression, which is still a valid Boolean expression in its own right, And now we can define the final problem, which is to figure out, given this edge I'm taking, what nodes will be masked, what terms will be masked. There is one intermediate problem in that, is that you might have more incoming edges. So if you have a bazillion terms, you will have a lot of short-circuiting. And if you have a lot of short-circuiting, you have a lot of masking effects. Because you can't have one without the other. Which again is shown by reversing the expression, right? And the solution to that is really to do a Cartesian product and filter. Because we can compare in constant time. It's very easy to just, sort them, right, and process them. So let's do that for this A and B and C program. This is one pair of short circuits and masking edge. And if you apply the masking thing, so if you take C to false, obviously A didn't matter, right? Because A is on the left and there are all ands between, right? And the same thing applies to B. If you take the edge C to F, then it didn't matter that B to C was true. But also, if you take B as false, then it didn't matter what A was. And of course, all that put together, like for C, you can just combine these two, right? This is the same expression as before, but I've substituted the B for an S, because now we're on the sub-expression. So this relationship has a surprisingly useful implication. And that is that if you define the first, start S, the first S, S0, to be the outcome, which you now have because you have the last term and the outcome, right? You have the successor function. Then you can, and really when you think about this, is the same problem we did when we found the expressions in the first and isolated the decisions in the first place, but in reverse. Now we have the outcomes and we need to figure out what terms are a part of this sub-expression, right? But now we know what the outcomes are. We didn't know anything about it other than the leading term when we went it from above, right? So then if you look at what nodes have both of their successors in the set of nodes I've already seen or collected. And if you start with the outcome, because of this property that all of the nodes in an expression will have its edges either to some other node in the expression or one of the outcomes, you eventually get to a fixed point by repeatedly seeing, what nodes have all of their successors in the growing S, where there are no more nodes to add, right? So this is a very, notation-heavy way of denoting something that's actually pretty easy to do by hand. So if you have this expression A and B and C or D, and this is our short-circuiting target. The short circuit is C to D, so D is short-circuited. Then we have the CT as a short-circuiting edge, and D to T is our masking edge. So taking the edge D to T would mask B and C. And here you can tell immediately, from being human, where you want to end up. You want to end up with B and C, right? So let's do it. We know that the last term in the expression we're looking for is C, right? Because it's the lower ranked of the two nodes in the topological sort. And we know that the outcome are the successors of this node, which are D and T, right? So this is the outcome we start by marking, which means that our initial 0 is D and T. And now I mark the edges gray. Those are the edges that go into our SN. And you can see C now is an orphan. No, sorry, it's not an orphan. It has no children anyway. What's the term for that? Anyone know? Pardon? Leaf. Thank you. It's a leaf. So that's really what you're doing. You pick the leaf, you remove the edge, obviously. It's almost like doing it from a tree, and then you look for new leaves. So that's what we're doing. So S1 is, you add the C, and then you remove the edge C to B. You do the same thing for B, but A still has an outgoing edge, right? So that's our limit. This is our fixed point. You can do this however many times you want, and you will never get a larger set than S2, which is D, T, C, and B. And then we remove our initial two outcomes, because obviously they aren't a part of the sub-expression, they're the outcomes. And what we're left with are B and C. Turns out this works for any graph. If you put it together in sort of algorithmic notation, if that's a thing, it looks something like this. Where the first two lines are pretty much just specifying what and how to iterate, right? But I think it's much easier to look at it in terms of, remove the edges from the graph. Or remove the leaves, and then obviously the edges that would go through that leaf, and then keep on removing till you're at the fixed point. This too is pretty easy to just straight up map to C++. I would do the Cartesian product is a nested for loop over the predecessors, where you do the if smaller or larger than continue. Right? The program just fell out. So let's look at some consequences and drawbacks of the algorithm and of the approach. So the good is that if you implement this in the middle end, it's useful for more languages. So it's largely been tested with C and some C++, because C++ have fun things like exceptions and, well, primarily exceptions, but also classes that can sometimes obscure things. I tested it for D. D has checked array access, bounce checks, which means that every array access now gets a conditional check, which is nice. Or not, depending. Which it does pick up on, and it's consistent with how G-cov operates with its branch coverage. The bad is that it's very sensitive to control flow graph construction, and that also means that currently it is useless in Go, because Go uses a different strategy for constructing the control flow graph, where it constantly folds booleans. I have an idea of doing data flow analysis on top of that to undo the work that the Go frontend does, and also to stop some programmers from cheating coverage doing that, which would be pretty cool. It would be an even stricter form of MCDC. And again, the bad is that it does pick up on an implicit conditionals, because may or may not want to have bounce check of every array access in your test suite. And some expressions are indistinguishable because their control flow graphs aren't the same. That may or may not be a feature. You can expect your compiler to do some term rewriting for you. So maybe that's cool. And then there's the beautiful. So I'm actually very happy with this program. The first draft, which was before I started trying to do the maths on this, was absolutely terrible, awful, and really didn't work. It was way too complicated, and it handled most of the special cases until I added one tiny one that broke the entire model, right? Because it turned out the algorithm was wrong, because I didn't actually understand the relationship in the graphs. Programs then has this natural way of becoming way much like higher level. So most of the operations in the actual algorithm itself, in the code in C++, are they're various sets, operations and graph traversals and searches, right? They're easy to understand, and then you can combine these high level operations, which are now simple function calls, rather than having to mask through or wad through hundreds of lines of loops and special cases and checks that don't really make sense to anyone unless you're deeply familiar with how it works. It turns out too that this is a pretty good opportunity for good naming, because now you actually have an intent that you're able to put into the name, and it makes code almost more malleable, because now you can do some implementation changes, but you also know that you need to say implement whatever variants the set operations would do. So you can do something other than a bit mask that would map back to some node array. You can do literally this with standard set if you'd like to, but you still have to obey the rules of the set, not of some maybe obscure implementation detail. And it also leaves a lot of room for cool optimizations that you can do, because they optimizations that are possible because of these set relationships, rather than maybe a cool trick that happened to work because of representation. And honestly, it's pretty fast to complete programs. Notice I didn't say write programs, but complete. Because I think if you consider writing plus the debugging and testing you have to do when you don't have a strong theoretical foundation for what you're doing, it's faster to type, but I think they're slower to complete. We do have a few minutes, so I would like to also mention how it's instrumented. But to be fair, this approach isn't mine. This I stole from the University of Minnesota and their Wallen and his guys. But the observation is that instrumentation has to be fast, right? In particular, because those that care the most for MCDC tend to also target embedded, which means that there are limitations to how intrusive instrumentation can be. And the good thing is that you really only need a handful of bitwise instructions in order to make this work. So remember that there is an ordering, like you can sort the nodes because of this topological sort. Which also means that we can sort B, right? So if you have a Boolean expression, you have a bunch of nodes that you know belong to the same Boolean expression, then you can sort them, right? And that also means that there is a bijection from the natural numbers to the nodes in B, right? So what we're doing is that we initialize 2 global accumulators for every decision, and roughly speaking that's an if, but you get them in the whiles, you get them in the do whiles, in the for, like anything that would change control flow. You get 2 global accumulators. You can fold these, if you want to save even more on space, into one and then use a protocol for which bit means what. So here they're represented by a 4-bit integer. In GCC, they typically use 64-bit for Intel. It's a variable with type, so it depends on your target architecture. And then there's an expression on the right, A and B or C, right? And since there's a bijection, we can do this. There's that A, the first term, is the least significant bit, B is the second one, blah, blah, blah. So if you then run it with 001, you now see what bits you set, right? So this is how the global accumulators work. And these are stored and persistent in between functions, and eventually this is what gets written to the GCO file. So you run it again for 000, and now you set the A for false. And then for A and not B or C, then you set these 2. The local accumulators pretty much behave in the same way, but remember that we have the masking thing. Oh yeah, oh, so by the way, so since these are integers, updating these masks is a simple bitwise OR, right? For the local accumulators, we need to do a little bit more. So what we do is that whenever you take, and this is what happens in the function. So you have, because a function is pretty much single-threaded all the way down conceptually, it is sufficient to have two accumulators, one for true and one for false, for all of the conditions in a function. So here we do save some space. So then what we need to do is that whenever we take an edge in the control flow graph, that is, we evaluate one value to true or false, we record that index of the edge that corresponds to it, right? And then we look into this masking vector, this table of masks, and then we see, will this trigger a masking operation? And then we just remove the things that had previously been set that would have been, that are now masked away. So in this case, E is the edge taken, and M of E are the nodes that would be masked when taking that edge. This is what it would look like in the binary for the function A or B. I picked up 2-term1 to just keep the example smaller. So you would have a prelude, which would reset your accumulators, the local accumulators. And then you just run the program, right? So you see, if you take the edge A, if A is true, then you update the true array with 1, right? And then otherwise you update the false array for A with 1. And then you either go to the true or to the B, depending on the value, right? And B has a masking effect. So if B is true, then you need to remove the value that would have been set by A. So that's where you do the AND before finally updating it with yourself. And of course, at the end of the Boolean expression, these are flushed, right, to the global ones. In implementation-wise, you need to add the instrumentation code whenever you're taking an edge to the outcome in order to satisfy, exceptions, and it doesn't matter too much, but that's where we insert instrumentation code. So just a handful of bitwise instructions, no branching, it's very fast. Yeah, that's really it. Any questions? Oh yeah, I have this one though. So some graphs will be indistinguishable. So A and B and C, and if A, B, C in order, if there are no else's, will be the same control flow graph and therefore have the same coverage report, which is not necessarily what you expect when you type it, because again, we've thrown away the syntax. But semantically, this makes sense, right? Semantically, these two are identical. All right, that's lunch. If you have any questions, or if you want to see how it works on the computer, grab me at lunch or between sessions, or come to the talk in a few hours. Thank you very much.